Hello. For those in the room, I'm looking up there because that's where the camera is. Hello to those watching online. I'm David. I'm the coordinator of the Maths Learning Centre, and this is Intro to Financial Maths, Semester 1, 2018. Hello from the past, those of you looking in the future. And that's enough of that. Okay, so it's IFM. I've had a couple of requests to talk about inverse functions and logarithms. But other than that, I have no other requests. So when I get to the end of that, you can ask me to talk about anything in the course, and I will try and do my best to give you what you need, or pick random past exam question or tutorial question or assignment question, and you want me to talk about how I would go about doing that. You can ask that too. At any point, feel free to stop me and ask me a question. Especially if you want to say, how did you decide to do that, David? That's the most important question you can probably ask if I'm doing a problem. I am, not immune to making errors, especially with minus signs. So if you notice one, please let me know. That's the rules. You can ask me questions. That's what this whole thing is about. So, all right. Let me talk about the inverse functions first. There's a weird... There we go. Okay, so I'm making this up as I go along, so bear with me. There's a big thing in this course about functions, and most of mathematics is built upon the idea of functions. And functions, in general, are this concept where you can take things and it spits things out. So you put things in and it spits answers out of some sort, and that's the idea of a function. And so you go, that's the not maths way of talking about what a function is. Okay, so there's a definition of function somewhere, I'm sure, but this will do. And you can think of it as a machine that you stick stuff into it and it spits stuff out. And you don't have to put one thing at a time into it. So if you're doing any economics courses, you might already have learned about utility. And in that case, you put two things in and it spits one number out. It's okay to have multiple things go in and one thing come out, but you can only have one thing come out at a time. That's the idea of a function. And you don't have to think of it as a machine. You can think of it as that everything that goes in has whatever comes out attached to it. It's much easier to talk about this with numbers, so I'm going to do it with numbers. So it's usually numbers in, and it spits numbers out. That's an O. And the usual way that it does that is via some sort of formula. And so you'll have some sort of formula. It'll be a number like x, and the number it spits out might be, x squared minus 5x or something. And so that's the classic way of doing a function. And the way we'd normally talk about that is we'd say that when you apply the function called f to the number x, it produces this answer, and you would say f of x is equal to x squared minus 5x. And so you read this aloud as of, and even though it looks like a multiplication, it's not. It's the function f is being applied to the number x in whatever strange way the function behaves and producing this answer. Okay. And so I can stick numbers in this position and say f of 3, just picking a random number, is 3 squared minus 5 times 3, which will come out to 9 minus 15, which would be negative 6. And so, in a way, this notation is giving a new name for the number negative 6. It's called f of 3. And, it's almost as if when the function looks at the number 3, what it sees is the number minus 6. That's my way of thinking about it. It's a personality sort of thing. And the other way of thinking of functions, so another picture, is that there's all these numbers you could have chosen. They're really supposed to be evenly spaced, I'm sorry. And you're supposed to be able to choose not whole numbers as well. and every one of them has a number attached to it. So when I put 0 into this formula, it comes out to 0. When I put 1 into this formula, it comes out to 1 squared minus negative 4. When I put 2 into this function, it comes out to 4 minus 10 is negative 6. When I put 3 into this function, it also comes out to negative 6. When I put 4 into this function, it comes out to minus 4. When I put 5 into the function, it comes out to 0. Again, when I put 6 into the function, it comes out to 6, and so on. Okay? And every number has an output attached to it. And you can imagine that if you want the function to reveal its number, you just stick it into the formula and it tells you what it is. But it's possible to just have functions where there's just a list of numbers, numbers that go in and numbers that come out, and there's no formula at all. And what we'd like to do in science and economics and engineering and all these other disciplines is to look at the numbers we have and try and imagine a formula that will come out to that. I mean, that's what a lot of what we're trying to do is model, based on the numbers we see, what the formula should be. And so in this course, they taught you about a whole lot of different kinds of functions so that hopefully in the future, if someone uses those functions to create a model, then you'll know what they mean. And you can expect that certain kinds of functions will have certain kinds of relationships with numbers will have certain kinds of functions. Okay. So this is an idea of function, but it wasn't very long when people studied functions until they realized that they could represent this graphically. I could represent this minus 4 as a distance downwards, and this minus 6 as a distance downwards, and this 6 as a distance upwards, if I wanted. And I could actually, instead of having those lines to tell me where things are, I could instead draw a graph and I could imagine going, I'm going to measure 6 up from here. It's going to be way easier if there's a ruler to measure against, and so I will draw a ruler here. A ruler here to mark our lengths against, and now I have coordinate axes, and I can go 0 here, minus 4 here, and instead of drawing a line, I'll just draw a dot where it comes to. Like that. And now we have a graph, or graph if you like, but I'm from New South Wales, so that's how I say it. And so we can now much more easily imagine what might have happened if we had figured out what it was at 4.5 and 4 1/4 and 4.1 and that sort of thing, and fill in the gaps between them. Like that. All right, that's the idea of a function. Sweet. So I needed to say that so that I could think about inverse functions as easy as I possibly can. So this is a graph. The beauty of what Descartes did when he invented the Cartesian plane here is that he managed to now connect geometry and algebra, which weren't connected before. People would draw pictures and with circles and compasses and rulers and stuff, and they would do calculations, but they would never see them as two parts of the same thing. And now we have this, and we can see that there's a formula here that says that whatever the y coordinate is x squared is the same as whatever the x coordinate is squared minus 5x. Okay, cool. So now let me actually talk about inverse functions. Back here I might stick a heading, functions. Okay, so inverse functions are, well, doing the same job but backwards. And it's a little easier to talk about them in terms of this diagram here. So inverse functions, if you have a big list of what number goes to what. So we had, I won't use that one. I'll just use 5x minus 1 if that's okay. So when you have f of 1, it comes out to 5 times 1 minus 1, which is 4. And f of 2 comes out to 5 times 2 minus 1, which is 9. and f of 3 will come out to 5 times 3, which is 15 minus 1, which is 14, and so on. And I could have a big list of all the possible answers it could possibly give. And they don't have to be whole numbers, but I'm on a roll now. And so on. And the idea of an inverse function is to try and do that backwards, to try and say, well, if I have this thing and I know how it goes this way, if I see a number, how do I get back to where it came from? So how do I figure out what goes in that position there? So I could totally do it as solving the equation. I could stick 5x minus 1 in this position and rearrange it to figure out what the x is. Okay, so what if I wanted to go backwards? So in that case, I might go, well, 5x minus 1 is supposed to be 39, so 5x is 40, so x would be 40 divided by 5, which would be 8. Yay! That's about it. Okay, and which is great, except I don't want to have to do that every time. What if I just had a big list of these numbers and I wanted to just automatically tell me where they came from? Well, that's a function. And a function is really just having a number and telling you which number goes with which. And so really I'm just saying, well, 4 goes with 1, but what if I want to do that backwards and say 1 goes with 4, and 3 goes with 14, and 4 goes with 19? So I want to do it backwards, and so I want a formula that will automatically tell me what this 8 is based on this 39. So let's see. I'm just going to guess what it is. Based on what we did in order to figure that out. In order to figure this out, we had to add 1 to the 39, and then we divided by the 5 to get the 8. So that's the process that I did in order to figure out how to go backwards here. And so that's the inverse function. So it's one way of finding inverses is to solve the equation and keep track of what you did to the number on this side here. So I'm going to make that a little bit more explicit. To get from here to here, I added 1, and to get from here to here, I divided by 5, and so I did that in that order. And now I had to put the entire of the x plus 1 on the 5, because that whole answer got divided by 5. So that's one way of going about finding inverse functions. Now, but that's just one example. And usually one example is enough for you to abstract what ought to happen. But most of the time you would like to be able to do it no matter what the number was. Oh, I should say, I pulled a Swiftie here. This x here is that answer. So I changed what my x was to be the 39 when I did this. I'm sorry that if that confused you, because it is one of the most confusing things about this. I probably should have called this by a different name. So what most people do when they're trying to find a function, an inverse function, that's the same thing, David. Like that. What most people do when they're trying to find an inverse function is they will do this. They'll say, okay, let y be the answer. And this tells us if I know what x is, I can figure out what y is. And I want to do that backwards. If I know what y is, I want to figure out what x is. So I'm going to rearrange this without having any plain numbers in there and try and get to where with just the x all by itself. So I could take the 8. I could divide by the 3. And then I could do the square root. Now here's where I run into trouble. When you do a square root, it only ever gives you the positive answer. But technically, a negative number could just as easily square to give, 9. I could have minus 3, then squared could be 9. And so I have to put a plus or minus there. And that's not going to work, because an inverse function, a function is only allowed to give one answer at a time. I said that right at the beginning, that when it spits answers out, it can only give one answer at a time. And this one is giving me 2 answers. For every y that I put in, I get 2 options, a positive one and a negative one. So this isn't actually going to be a function at all. So this one at the moment doesn't have an inverse function, because there's 2 answers. I have to say there's no inverse. Yep?
What if you put absolute value of x? Is that still not?
Well, you still don't know exactly what x actually is. So, I mean, that's a great plan. Like, if you did the absolute value of x, there'd be, the plus or minus would go away. It'd be great. But that's just telling you that the absolute value of x is this answer, and there's still 2 x's that go with that. So it's a really good idea, but it doesn't actually solve our problem, unfortunately. So, yeah, there's no inverse here. So if you really wanted an inverse, you would normally go, oh, well, this is an economics thing. The x isn't allowed to be negative anyway, and so you'll just do the positive one. So usually what would happen is that it would be something like, find the inverse function for f of x is 3x squared plus 8 with x greater than or equal to 0. And they'll say something like that. It won't be 0, actually. It'll be, oh, crap. Just a second. Give me a moment. It'll actually be... David, don't make up examples on the spot. It never works. Just give me a minute. Yeah, 0 will be fine. Okay, it's all good. 0 will be fine. And so you have this. And so you'll get exactly the same working. Let y equals 3x squared plus 8, blah, blah, blah. And I'll get that thing there, which is great. We have the same problem though, but we were told that x had to be greater than or equal to 0, and so we can ignore the minus 1. So that means that when I do the function backwards starting at y, then the answer is this. That's basically what that means. Now, one of the things about mathematicians is that they are completely happy with any letter representing whatever they want. So at this stage, I'm going to start thinking about it as saying, well, this is just a function. There's nothing stopping that y from being whatever number I want. I mean, there's only some numbers that are actually going to work, because this thing, the y has to be positive as well. But I'm now going to say I can do it with an x if I want, because I can put whatever number I want in that position, including x. So at some point, you make it to be about x. It depends on the situation that you're in. So over in economics, where everything's in p's and q's, you just leave it. I mean, you go, well, the inverse, you do it on q and it gives you a p, and you do the original function on p and it gives you a q, and you don't switch the q's and the p's at any point because you don't care, because they mean something. Whereas in a lot of mathematics situations, well, none of this means anything. It's just, it's just maths, and so you can put whatever letters you want. So just be careful if you're doing a sort of a word problem or something that you're actually using this for in a different course. It's not traditional to actually change your letters. Just pointing that out. Yeah. Just look closely if you've got an exam question and it wants the inverse. And check to see if they want f inverse x, or if they just want the inverse. If they just want the inverse, then it's fine to write it however you want. But if they want f inverse x, you have to put the x in. So read carefully what they've asked you to do. Okay. So that's inverse functions, and there's not really much more to them than that. You can draw what the graph will look like if you have an inverse function, and most of the time when people read graphs in science and economics, they don't actually do the thing that I'm about to do. That is such bad writing, I'm sorry. Inverse function graphs, the idea is that the original function will be whatever shape it is. And then, oh, I can use my plastic sleeves. This is so exciting. So most of the time, if you're reading this stuff on an actual graph, like in a textbook or a journal article or whatever, and you know which x gives you which y, and so you go, oh well, when x is 4, I come up here and y comes out to be 5. And if you want to do that backwards, you just do this. Like you just read it off the y-axis and go down to the x. And so you can do, you don't need another graph of an inverse function at all. That's not at all necessary in most situations. But you may want it to always have the thing that you put in on the x-axis and the thing that comes out on the y-axis, because that's tradition. And so you would go, that really looked like it was going to be blue. Someone switched my lids. So what will happen is I will switch it this way. I'll do that again. I flipped it diagonally. So what I'm actually flipping it around is this line here where y is equal to x. And I went, all right. I flipped it in the line y equals x, and that produced my inverse function. So the green line there, now if I'm very good, I can trace this. So the green line was y equals f of x. And orange, and the orange line is y equals f inverse of x. There you go. That's how to draw. Plastic sleeves are wonderful. You need a whiteboard marker for it to work properly. So that is what the graph of an inverse function will look like. What a lot of people do is they actually just draw this line and then they sort of draw diagonal lines this way and copy it one side to the other. So if I was going to do that by hand without tracing a plastic sleeve, and they don't have to be curved, they can be straight. I could draw in my line y equals x, which is supposed to be straight, and then copy everything from one side to the other. So I'll go, that one stays the same, that one stays the same, that one stays the same because they're on the line. This one will have to come this way, that way, that way. All right, we're doing pretty well. This kink will come here, that one will go over there. So you can switch it going across that line there. Sweet. That's what the graph of an inverse function looks like. I haven't quite drawn it correct because this shouldn't be going down if it's probably about like slightly upwards. Okay, that's the graphs of inverse functions. That was fun. Never used the plastic sleeve in an actual lecture before, so to do that. So I'm so super excited. Okay. Which leads me to the inverses of certain functions. So some functions have names for their inverses already. So inverses of classic functions, if I have that for x greater than 0, then the inverse is that. Technically, x squared doesn't have an inverse because I've got two options. It could be plus x or minus x, minus root x. I don't even have to do the formulas, like the algebra stuff that I did, to tell that it doesn't have an inverse, because I can just declare that f of 1 and f of minus 1 are the same answer, and so I'm not going to be able to go backwards because I don't know which answer it's supposed to be. What are some other classic inverse functions? Just as an example there, if you've got something with a number power up there, and you know what that number is, then the inverse is 1 over that power. So technically this one is x to the power of a half, the root x. So if this had been a 7, that would be a 1 over 7. If this had been a 4, this would be a 1 over 4. And the odd ones, you don't have to specify whether x is positive or not, but the even ones you do. So, yeah. Okay, don't need to do that. Did you do trigonometric functions in this course? Like sine and stuff? Nope, good. Technically they are relevant to some economic stuff, because things that go in cycles have certain kinds of functions, but they must have cut it out. Maybe it's next semester. I'll have to look that up. So if I had something that was instead 2 to the power of x instead of x to the power of 2, where the unknown is up in the power instead of down at the bottom, then the name of the inverse function is this. Right. And the classic one is e to the power of x, where e is an irrational number, it's about 2.7. And the name, you would think that it would be called, you could say log ex if you wanted, but it's just what they call it is ln. So it's short for log natural, because it's French, it's logarithme natural, which, because otherwise in English we call it the natural log, which would be NL, but it's French, so they put it in the other order. Okay, so that is not an I. It's really common for people to think that's an I if they've never heard it said aloud before. So they think it says in. I think it's a capital I. It's a small l. Some people pronounce that aloud as ln. I pronounce it ln, as in, you know, daytime talk show host. Bad joke. I have to put it somewhere. Okay, so classic. The reason why this number e is so important I'll probably get to eventually, but I want to talk about this a little bit more, this sort of relationship here, and what this function is at all. So let me just talk about those power functions. So let's see. So let's have a closer look. So 2 to the power of x has all these wonderful properties. Or just any plain number to the power of x. We need a positive number for this to work properly. So the idea behind this function is that 2 times x goes up by 2 every time x goes up by 1. Whereas 2 to the power of x multiplies by 2 every time x goes up by 1. So this is my table. You have 1, and it comes out as 2. And you have 2, and that comes out as 4, and this one comes out as 8, and this one comes out as 16, and this one comes out as 32, and so on. Every time this goes up by 1, this times is by 2. That's how the powers work. And it is technically possible to fill in the gaps. And I can work backwards to this, right? So if this times is by 2 going this way, then going that way it should divide by 2. So that's why when you do 0 it comes out as 1, because when you go forwards it should times by 2, and the only way to times by 2 to get to 2 would be to start at 1. And that actually tells us what to do for negative numbers as well. We can work backwards. If we go back to -1, it should divide by 2 again and give you a half. And if we go back to -2, it should divide by 2 again and give you something else. So I can follow this pattern. The hard bit is filling in the gaps in between them. So what happens if you put 0.5 in here? It's got to be a number somewhere between 1 and 2, but which number is it? And that would be the square root. And so we have all these ways of finding out what's in between. But it was invented first for whole numbers. So some useful other things, you know, if we put in -1, we get a half. And if we put in -2, we get a quarter. And you just keep dividing by 2, the more negative it gets. And if you put in, I just want them on the same page. And if you put in a half, you get the square root of 2. And if you put in a third, you get the third root of 2, and so on. And, you know, 4.7 will be somewhere between 16 and 32. Probably closer to the 32 than the 16. So, you know, 4.7, you know, between 16 and 32. It's not a particularly small range, but you can get the exact number if you actually figure it out. That's what calculators are for. They're programmed with this stuff in it. So what we want to do when we do the inverse is do this backwards. So when we do the inverse of this function, I want to do all of this backwards. So I want to say, I'm going to take my table. Log base 2 should do this backwards. So it should be that when I do 1, it should produce 0, because I'm going to do it backwards. And when I do 2, it should produce 1. And when I do 4, it should produce 2. And when I do 8, it should produce 3, because I'm copying this table exactly in reverse. And when I put in a half, it should produce -1. So it's literally the inverse function. And so it does this backwards. And so while this function gets really big really quick, I put small numbers in and you end up with really large numbers very fast. This function is the reverse. You put in sort of big numbers and they still get bigger but not very fast. So to get to 4, I have to put in 16. And to get to 5, I have to put in 32. And so the more I want this to be, the bigger this is going to have to be. It's the exact reverse of this. Okay. Computer scientists are into the log 2s because everything in computers is counting on and off, and so there's only 2 options. And biologists are into the log 2s as well because they're really interested in when like a population of bacteria doubles in size, and so they're interested in doubling, and therefore they're interested in log 2s. Whereas most scientists are much more interested in log 10s. They want to know when something's 10 times bigger. Measuring earthquakes, the Richter scale, when you get a 4 on a Richter scale, that's 10 times worse than a 3. That's a log scale. Okay, cool. So this is nice. So we have these functions, and it's great, and we can draw graphs, and we can sort of try and figure out what the answer is. And so, as an example, I could do this, right? I could say, what is log 5 of 158, for example? I could try and guess what that is. My calculator isn't going to tell me this, because my calculator doesn't have a log 5 button. It's got a log button, sure, but its log button, which is here, is log 10. You'll notice on mine it has a little 10 to the power of x above the log. Well, that's to say that these 2 functions are inverses of each other. And so this log is actually log 10, because it's the inverse of 10 to the power of. It does have an ln, and that's e to the power of. They're the opposites of each other. But it does not have a log 5. So I would have to estimate this. So if I wanted to, if I wanted to estimate what log 5 of 158 was, I would go, all right, well, let's just see. 5 should go to, like we're doing 5 to the power of backwards, right? So if this is x and this is 5 to the power of x, so that would give me a 5. That would give me a 25 because I times by 5. That would be 125. And this one would be, right, it's too big. I'm in here somewhere. 158 is in this zone between these two. So my first guess at what log 5 of 158 is that log 5 of 158 must be between 3 and 4. Because 5 to the power of 3 and 5 to the power of 4 are on either side of 158. So if I wanted to estimate this to within the nearest whole number, could totally do it. And if I wanted to get it more accurate, I could just keep trying different numbers, right? I could go, ooh, well, what's 5 to the power of 3.6 and see what we get. That I can do. 5 to the power of 3.6 is 328. Still too big. Okay, so 3.6 is too big. And I could just narrow it down if I really wanted to go to all the effort. But there is a way of getting your calculator to just tell you the answer. But to do that, I'm going to have to talk about some of the log laws. So I'll get back to that. If I forget, please let me know. And if we all forget, then, well, it wasn't really that important. Okay. I'm just going to move my finger over. Right. So let's talk about the rules of how these things work. So I'm going to line them up next to each other. The power rules and the log rules. Most people call the power rules the index laws. Okay. All right. So with the index laws, I'm just going to do them all with 5, if that's okay, rather than with letters, because it's easier for me to process it if they're numbers. So 5 to the 2 or times 5. Damn it. I want a bigger number, if that's okay. Sorry, I'll do them with 7s. Okay, so if you multiply 2 that are both 7, then what will happen is they'll add. So 7 to the power of 2 times 7 to the power of 3 is 7 to the power of 2 plus 3. And if you divide things, 7 to the power of 5 divided by 7 to the power of 3 will be 7 to the power of 2. And division becomes subtraction. And powers of powers becomes multiplication. 7 to the power of 5, then to the power of 3 is 7 to the power of 15. They're your basic log laws. The index laws, sorry. The log laws are the same but in reverse, and I'm actually going to do them with symbols in a minute to really point out what's actually going on here. So the log laws are the same but in reverse. So log 7 of, I don't know, 8 didn't give myself enough space, did I? So look at this. Times on the outside here was addition up in the power. And in this one, times on the inside is addition on the outside. In fact, I've written it backwards, right? This one had the powers on this and the answer here, and I've written this one in the reverse order. I didn't mean to do that, I'm sorry. So subtraction, now division on the inside is subtraction on the outside. And powers on the inside is multiplication on the outside. So look at this one. Multiplication on the inside was powers on the outside. Powers on the inside was multiplication on the outside. They work in opposite directions. I'm going to do them with symbols now. X to the A. I'm going to write them in both directions so it's easier to see what's happening here. So that's one of them. And for logs, it's the other way around. Oh, that would be an X, wouldn't it? Yeah, I don't like putting an X in that spot. I'm sorry. So same deal. In here, addition up the top is multiplication down the below. Multiplication down below is addition up the top. I've just written the same thing in the reverse order. Multiplication on the inside is addition on the outside, and addition on the outside is multiplication on the inside. Subtraction on the inside is division on the outside for powers, but it's the other way around for logs. Division on the inside is subtraction on the outside. And we can do it just as easily writing it backwards. I know it seems like overkill to write it both ways, but it just makes me feel better. So one more rule. X to the A and then to the power of B is X to the AB. And log n of A to the power of B is B log n A. These two don't look as similar as the others, but it's the same idea. So that seems like a lot of rules, but I have in my head the order of operations. And this is how I remember which one is which if I'm called upon to do it. I'm actually quite good at doing this one without remembering any rules. I'm really familiar with this one and I can do it, but with the logs sometimes I don't do it right. And so if I'm trying to do it really fast, so I know this one. So when you do the order of operations, you know that plus and minus are the last thing to do. This is like what in South Australia people would be taught as BODMAS or BEDMAS in South Australia. And if you're from the USA, you'll know it as PEMDAS because they say parentheses and not brackets. Or please excuse my dear Aunt Sally, which is the first letter of each. It's so bad. So plus and minus at the bottom, times and divide are next, and powers and roots are above. And that's how I write a power, because on a computer that's what I'd type in to get a power. So with exponentials, or the index laws, I know that plus on the inside is times on the outside. But with logs, this is the inside and this is the outside. And it goes one step. So I know that powers on the inside is multiplication on the outside. I imagine that actually square roots on the inside would be division on the outside. So if I did like the square root, that would be dividing by 2. So this is how I remember it. There you go. I don't know if that helps you, but it might. I find it useful. And the other thing I know is that log moves really slowly. You have to put really big numbers into a log to get a moderately sized number out. And so it tends to make big things into small things. And so big things like powers on the inside become smaller things like times on the outside, because that's what logs do. Whereas powers tend to take small numbers in and spit big numbers out, and so they make things bigger. So plus on the inside becomes times on the outside, because times is bigger than plus. There you go. I've never said it that way before. That really appeals to me, actually. Okay. There you go. That's what logs and exponentials are for. And therefore, we should really do a couple of solving equations sorts of things with logs. Let's see. Oh, there was one more log law that you need to know, and it's this. Log b of a can be converted to any other log by this process. And in fact, I'm going to convert it to ln. So let me give you an example of using that. Log 5 of 158 that we were calculating earlier should be ln of 158 divided by ln 5. So ln of 158 divided by ln of 5 is 3.146 to 3 decimal places. I told you it was between 3 and 4, so it's at least in the correct zone. If this really is the correct answer, then I should be able to go 5 to the power of this should give me 158, because that's the idea here. Because I figured out that it was between 3 and 4, because I know that 5 to the power of 3 was at 124, it's 125, which was too small, and 5 to the power of 4 was 625, which was too big, so it had to be between. So if I do 5 to the power of 3.146, 158.1. Awesome. It doesn't exactly because I rounded it off. Yes, the world makes sense again, just to check. 5 to the power of 3.146 is 158.1. Nice. Yay. Just to go all Spanish on it. Okay. Or in Spanish, you put an upside-down exclamation mark at the beginning. Haven't you ever seen Dora the Explorer? Okay. So, of course, they don't say yay. I don't know what they say in Spanish. I'll have to look that up. That'd be cool. The only word I know off the top of my head in Spanish is vámonos, because of Dora the Explorer. Vámonos, let's go. Okay, so we can convert any log to any other log using this information. And what that means is that we really only need to know ln. We don't really need to know any other logs, really, because we can convert anything to ln if we want, which is extremely useful for solving equations. So there are equations that you sometimes have to solve that involve logs, in finance stuff. So here we go. Let's solve that. So logs are really useful for solving equations where the thing that you want to find is up in the power. So the first, if I want to talk about my decision-making process, normally when I look at these equations, I think about the order of operations and I think about what the easiest things to get rid of first are. And I would go, well, this 102 has got a power of n. The powers are sort of the strongest thing, and then multiplication. So it seems like getting rid of the 150 is going to be easier first, so I'll divide by that. Whatever that is. It's not going to be pretty because 15 doesn't actually go into 200. Yeah. Oh, sorry. I crossed out the zeros in my head. Sorry. I could have divided by 5, I suppose, as well, but whatever. I'm just going to leave it like that. And then now I need this n to come out. And the quickest way to get a power out of the power is to do a log. So I'm going to do this. So this is where I was on the new page, just so it's easier to read when people do this. And I'm going to go ln of all of this like that. Just do ln on everything, because I can do, these two numbers are the same number, if I pick the right n anyway. These two numbers are the same number, and so if I do ln to both of them, the answer will be the same answer. And the major log law that I can use to do this is the log law that says that powers inside is multiplication outside. Like that. And so therefore, n is ln of 200 over 15 divided by 200, ln 1.02, which is whatever it is. Let's ask the calculator. $130.8. Close enough to 1 decimal place. So if that was like a compound interest thing, we need 130 periods, whatever the periods are, 130 months, maybe just like, you know, nearly 11 years. Yay. It's not too bad, I suppose. It depends on how long you're willing to wait. Okay, that was the major use of logs for solving equations, is to get powers down out of the power. I just want to do it a different way, just to illustrate how the log laws work, even though this is not how you would normally do it, but just to show you that it will still work out anyway if I'm e.g. alternative. Let's have a look at this. So what if I saw that thing up in the power and I went, yep, logs is going to do that, and I did the logs first before I did anything else? What if I did that? Not what I would normally do, but what if I did? Well, then I would still have to deal with the fact that the n is inside here, and I can't bring the n down because this doesn't have an n. And so the only thing I'm going to be able to do is notice that there's a multiplication here and separate it based on that. because multiplication on the inside of log is addition on the outside. All right. So I really don't want this here, so I should subtract it. And then I'll still have to use my log law to bring the n down. I probably don't need that bracket. And then n will be that divided by the ln 1.02. Okay, which should be the same answer, yeah?
Also, just wondering, is it in the answer exam, is there a difference if I say log or ln? Because I never use log.
I don't know. If
Try ln.
I'd go ln. I like ln.
It doesn't matter.
Nah. If you say log, most people will assume you mean log 10. But some mathematicians will think you mean, and over in economics, I think they assume you mean ln anyway. I don't think anyone will care. If they have used ln in the question, you use ln. But if they haven't specified, do what you want. Just write log. So yeah, sometimes people just write the word log without an ln. It'll just be, without a number next to it, it'll just be log. Your calculator thinks that means log base 10, but something like Wolfram Alpha normally assumes that means ln. So do what you want. I'm sure it'll be fine. I can't guarantee what will happen, but I know that there are some of the math lecturers who say, no, I don't like ln, we'll just use log, and so they'd prefer it if they were marking it. So yeah, do what you want. If you like log, use log. If you like ln, use ln. What you can't do is write ln 5. Like you can't write this. Because ln is specifically log e. So you can't do that. If you want log 5, you must write the word log. So that's important. Yeah, this is not a thing. But so if you really want this, then you must write that. But if you don't want to specify what this number is, just do ln, that's fine. Okay, cool. This is the same answer as we got before if you actually calculate it. And the reason is, look at this. ln of 200 divided by 15 is ln 200 minus ln 15. And if I had not cancelled them out, then it would have been ln 2000 minus ln 150 because of the division inside and subtraction outside, which is exactly the same answer as I have. So it'll all work out fine if you do it in a different order. But this one that I did first is ever so slightly quicker. So that could make all the difference. So I'm just going to make a note, a notation note. You can't write this, but it's usually okay to write just log in the place of ln x if there's no number. So if you don't like using ln and you just want to use log all the time, go for it. All right, so before I move on from that, does anyone have anything else they want to ask about or say in relation to logarithms or inverse functions? Give you some time to think about that. I'm trying not to get your lecture notes all messed up. those of you who don't have anything else about logs to ask, you could be considering other things you would like me to talk about, because I've still got 45 minutes. Yeah? Easier to show me?
Yeah.
I'll come there.
Sorry. It's that one and that one.
Can I borrow this from you?
You can take it.
Okay, cool. So nothing else about logs? Sweet. Okay, I'll call that closed off. If you ask something else later, then that's fine if you feel inspired. I'm just going to start a new page so that I can put the whole logs and inverse functions thing in its own PDF when I put it on the website. So I might just do some miscellaneous questions if that's okay. So I've got some stuff from, and so supply and demand, q squared plus 3, that's the supply, and the demand is p is 21 minus 3, and that's the demand. Okay. I learned recently, because didn't really know much of the economics, and I had a big chat to Stephanie McWhinney recently, and she told me all about this supply and demand, and this is like the average for all the people in the economy who are making decisions about whether they want to buy stuff, and all the suppliers, as opposed to an individual person, which is kind of really cool. It still doesn't make very much sense to me, some of the things about how this is produced, but yes, anyway, that's economics and not mathematics, so I'm okay with that. So we find quantity and price. Okay, cool. All right. So I don't know if this is the most efficient way, so I'm just going to run with it, and you can see how I would normally think about this. So the first thing I would think before I even attempted to solve this would be to think about what the graphs look like. So in economics, you put the quantity down here and the price up here, and q squared plus 3. Now q squared is a quadratic, and so it would be sort of like this shape. And q squared plus 3 would be a bit higher. So I'm thinking that's my supply. And the demand is 21 minus 3q, which is a straight line because it doesn't have any powers on the q. And it starts at 21 and goes down by 3 for every q, so it's going down something like that. So that's it's not an accurate graph, it's just a sketch. And that's fitting what I would normally expect to be true about supplies and demand. Supplies generally go upwards as the quantity demanded. Supply price tends to go up this way and demands tend to go down, so that's good, and I expect them to meet just here, and that there is where is the equilibrium. Oh, and do you know what? I'm not going to write it there. I'm going to write it here. And that equilibrium has a q coordinate, which I think is traditionally called q star, and it has a p coordinate, which is traditionally called p star. Okay. And that's the thing that we're looking for. So there we go. So I'm expecting it to be higher than 3. Because when q is 0, p is 3, which doesn't make any sense, and these models don't always work at the edges. But I'm expecting it to be higher than 3, because this is 3 and it gets bigger there. And lower than 21, because this is 21 and it goes down from there, because that's where it hits the up axis at 21. So somewhere between 3 and 21. So it's good if I get something other than that, I know I've done something wrong. So this is the sort of thing I do think in exams and in situations where I'm asked to do this stuff on the spot. I think about what I expect the answer to be so that I'm pretty sure when I get there, at least if I've done something wrong. Okay, so let's see. Well, to find the equilibrium price, this curve has the same P and Q as this curve. So at equilibrium, we're going to have that the two P's are the same. The supply P is the same as the demand P. And so I've got that Q squared plus 3 is 21 minus 3Q. And now I have to solve it. Yay. Okay, so now this is a quadratic equation. It's got a Q squared in it. I expect it to have two answers. Quadratic equations are easiest to solve if I put everything on the same side and leave a 0 behind on the other. So Q squared plus 3Q minus, what's 3 minus 21 would be minus 18. Okay. And so the quickest way to solve things that are equal to 0 is write them as a multiplication. And so I need to factorize this. So I have choices. I can either attempt to think of something that multiplies to give 18 and adds to give minus 18 and adds to give 3. Oh yeah, I can think of something actually. Or I can use the quadratic formula. So let's see. So I know that if I multiply 3 and 6, I get 18. And so I could do that. This is scary because it's coming out to 3. Have I done that right? Let me just see if I've got this right. I do not like it, Sam, I am. I'm distressed. If anyone has any thoughts on this, let me know. So that's Q squared 6Q minus 3Q, and 6 minus 3 would be plus 3. And then minus 18. Oh, it does work. So either Q minus 3 is 0, which would make the Q equal to 3, or Q plus 6 is 0, which would make the Q equal minus 6. And it can't be minus 6 because it's a quantity of things. And so that would make Q equals 3, which is not matching with my expectation that it should be more than 3. I'm not happy about this. Well, let's just see. When Q is 3, do they actually match up? Let's just check. I'm just going to say, Q can't be negative. Oh no, it's all good. The world makes sense again. That's a P equals 3. Q is 0 at that spot. Ah, right. The world makes sense again. I was looking at the wrong axis. That's where P is 3, but we should still check. So Q equals 3. So let's just check. P equals 3 squared plus 3 is 9 plus 3, which is 12. P equals 21 minus 3 times 3, which is 21 minus 9, which is, 21 minus 9, which is 12. Yes, it checks out. Okay, so our Q star is indeed 3. And in fact, we've just figured out the matching price that goes with that Q. It's 12. Because we subbed the Q into the formulas and they both came out to 12, and so it's correct that they're at equilibrium then because the price is the same, and that price is 12. How are we feeling? What I hoped to show you there was some of my decision-making processes about telling if I have the right answer or not. And also, not that I meant to do this, but proving to you that even maths lecturers can sometimes be thinking about things in the wrong way and fix it as they go. So too can you. Okay, so the next example question that I've been asked to go through is this one. So for which k does the following system have infinitely many solutions? Of course, doing random questions stuffs up the way I've organised the web page for you guys, so there'll probably be just a miscellaneous stuff at the bottom that you can find this video in. Of course, if you're watching this online, you've already found it, so well done. So for which k does the following system have infinitely many solutions? Okay, so that's the question. All right. So to tell how many solutions there are, I should try and solve it. And so if I was going to try and solve this, I would produce as much of the identity matrix as I can. And so I get that's a pivot column there, and there's a pivot column here, and I would attempt to put a pivot column in this position as well, which means I need a 1 here. And if there was, and it doesn't really need to be a 1 at the moment, because if this number turned out to be, say, 7, then I could just divide by 7, and it would be a 1 eventually. So I just need this number to not be 0 if I want to get a pivot in this position. So if there was a pivot in this position, then there would be a unique solution. So I'm going to try to write that down. If there's a pivot in the 3, 3 position, that would make it a unique solution. Okay? And the only way there could not be a pivot in that position is if that thing is 0. So no pivot in the 3, 3 position when k times k minus 3 is 0. Cool. And if k times k minus 3 is 0, that means that k is 0 or k equals 3. All right? So that's what we have so far. So far we know that it would have a unique solution unless k is 0 and k is 3, and we're looking for infinitely many solutions. So we have, those are our options, and we should just see what happens when k is 0 and k is 3, and see what it looks like. So when k is 0, 1, 0, 0. It's probably not necessary to write out the whole thing, but I just feel better. So when k is 0, we get that. And when k is 3, we get and 3 squared minus 9 is 0. Okay, that's what we get. And what I was doing is I was substituting, can I fit them both on the screen at the same time? Yes, I can. I was substituting my k equals 0 into this formula and my k equals 3 into this formula and getting what I get. Now, I probably didn't need to know the whole matrix because that last row is enough to tell me what's happening. So when k is 0, this last row tells me there's no solutions because this is like 0x plus 0y plus 0z equals minus 9, which is impossible because you can't make 0 equal to minus 9. That doesn't make any sense at all. So this would be no solutions. And this one, we've got a pivot here, pivot here. There are, in fact, solutions, but there's not a pivot in every column. So when there are solutions and there's not a pivot in every column, that means there's infinitely many solutions. So there are solutions. There's a column with no pivot. So that means infinitely many solutions. And so therefore, it looks like when k is 3, there are infinitely many solutions. So, when k equals 3, there are infinitely many solutions. Now, I normally, if I was doing this in an exam, I probably wouldn't write all of that stuff down. I would probably just go for it and maybe be a bit sloppy about it. But this would be a full solution, which would be extremely clear to anyone reading it what you were thinking at the time. All right, before I move on from this, I reckon it would be good to ask some what-if questions about this question. So, what if it was different? Before I forget, I'll give you your phone back. So I'm wondering what I would have to arrange in order to mean that it would be impossible to get infinitely many solutions no matter what k was. I'm wondering how I can change these two so that it's impossible to get infinitely many. This is the idea of doing what-ifs like this is really useful for making sure you really understand what's happening, and it sort of creates new problems for you to solve that nobody gave you. And so you tend to be better at recognizing what to do in exams if you spent time doing this sort of thing. So that's why I'm doing it now. So here's a question. What to get no way to have infinitely many solutions? So I'm going to write this down and I'm going to ask you guys to help me do it. I don't want all the answers, I just want an answer. How could I change this so that it was impossible to get infinitely many solutions? It's all right if you can't think of anything, but if you've got some ideas, let me know. Partial ideas are perfectly acceptable in this sort of seminar. Maths Learning Centre, you can have, everyone deserves to be able to talk about what their understanding is right now, even if it's not complete. So, thoughts? How could I change my question so that the answer would be there are no k's that give you infinitely many? Got an idea? I'm going to look back at what we had. The thing that made it turn out to have infinitely many solutions was that when this one was 0, so was this one. So I reckon all I need to do is change this number. Yep.
But then what if you had like a really small point number that actually squared equal 8?
So that's a good question. Let's have a look at that. So you're saying, well, what if k squared was 8? So it was like whatever the square root of 8 is. So k was the square root of 8. So about 2.83. Okay, and that would totally put a 0 in this position here. But to get infinitely many solutions, I need a 0 in this position here at the same time. But then the last line would be 0, 0, and 2.83 times 2.83 minus 3, which would be times the answer minus 3 would be minus 0.49, and that's okay. I'm going to get a unique solution then, because I end up with a pivot in that last position. So I actually end up with, just to do the whole thing, to get the whole matrix, I end up with this, and I can divide by that number and make a 1 in this position, and I get a unique solution after all. So that's one of the reasons why I did this what if. The only way to get infinitely many solutions for a 3 by 3 matrix is to have both of these 0 at the same time. And these can't be 0 at the same time. If this one's 0, then that one works out to not be 0. And if this one's 0, then that one works out to not be 0. So it's impossible to be 0 at the same time, so therefore there is no k that makes it infinitely many solutions. Sweet. Good. I'm glad I did it then. And that's unique solution. So just the moral of this tale, to get infinitely many, need them both to be 0 at the same time. And that's not actually possible in this particular one. But in the other one it was. Sweet. There you go. Look at how wonderful this what if thing is. So, you guys I think had a question. Yeah. Sorry? Yep, that's fine. Well, we've got all the devices today. Oh, past exam. Oh, hate big matrices. There you go. A storage shed consists of 4 walls and a roof, where the walls and the roof are made from an aluminium sheet and reinforced with 4 braces, so that each brace is held to the sheet with 6 bolts. The final assembly joins the walls and the roof together using a total of 20 bolts. Sure. There's a lot of words there. The following matrix describes the parts listing for these sheds. Shed wall, roof, aluminium, brace, bolt, shed wall, roof, aluminium. So I'm presuming that these are just abbreviations for them. So SWR A for aluminium and BR for brace, BO for bolt. Okay, cool. So I'm just going to check to see if I can read this matrix correctly, but I might want to write it down on the page so that it will end up in the notes when I do it. So I'm just going to keep this for a bit. This is 2012, apparently, this exam. And does the phrase parts listing matrix mean anything to everybody? Like that's actually been part of this course this year? Good, just checking. So first thing to check in a past exam whether the topic's still in the course. I've had people come before and go, oh, what about this? Yeah, that's not in the course anymore, so don't stress about that. One of the major reasons to go to at least watch all the lectures so that you can be sure what's still in the course from the past exams. Okay, so we have this matrix, so shed, wall, roof, aluminium, brace, bolt, 0, 4, 1, 0, 0, 20, 4, 0, 0, 1, 4, 24. 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0. Okay, so if I'm interpreting this matrix correctly, this is telling me how many of the other things I need to make each of these things. So to make the shed, I need 4 walls and a roof and 20 bolts. And to make a wall, I need 1 piece of aluminium and 4 braces and 24 bolts. And to make the roof, I need 1 piece of aluminium, 4 braces and 24 bolts. To make the aluminium, I don't need any other stuff. That's like a basic piece that the other bits are made of. To make a brace, they come as they are, so I don't need any other stuff to make them. And to make a bolt, I don't need any other stuff to make them. And so each column is telling me how many of the other things I need to make it, but not in total. It's just about the actual pieces I need. I'm thinking in my head of a wonderful diagram that might be helpful, that I have never tried to draw before. So we have the shed, and it's made of 4 of the walls, and 1 times a roof, and 20 bolts. And then the walls are made of 1 aluminium, 4, crap, needed more space. And then the walls are made of 1 piece of aluminium, 4 braces and 24 bolts. And the roof is 1 times aluminium and 4 braces and 24 bolts. I like it. This makes sense to me. So you don't include all of these bits in this column here. You only include the layer below where you are. So the shed includes these 3 pieces, but I don't include any of this in the sheds column. I only use this row. So I can imagine things that were made out of other things even further down, and each one would just use the layer below it to make its column. This makes me feel extremely happy, actually, to have thought of this. It might even be in your lectures, but you know, most ideas aren't new. Okay. All right. So I'm thinking there's got to be some sort of like process, and I'm going to have to look it up because I don't remember it off the top of my head. I only get to do parts listing once a year. So, you know, inverse functions are in IFM and Maths 1M and Maths 1A, so I get to do them, you know, every semester. But this I only get to do once a year, so I'm going to have to look it up. And I dare say it's in the algebra bit, and it's right near the end, isn't it? Have we only just done this? I can't find it. If anyone knows where it is in the notes, I would appreciate it. I can't find it in your notes, I'm sorry. Okay. So is the Leontief economic models are before it? Okay. And maybe it's like a subset of that. So maybe it's just like a kind of... I don't have that in yours. I'm sorry. Not that I can see. I could be wrong. borrow that. That's all right. That's all good. Let's see what the notes say. Each industry, we now have a different problem, manufactured products by one industry. One of my many components, these components may themselves have many components. Aha, that's my little tree diagram that I drew with the little things having more and more components. Good. May I say a complete product as well as some components. For example, a laptop factory might sell complete laptops as well as individual hard drives and batteries. Okay, so in our case, our guys might sell completed shed packs, but also just individual walls. Okay. Some items may not have any components. They're primary items. Oh, good, I've got a terminology for the thing I was trying to come up for a word for before, like things that don't have any other parts, called primary items. I should pop that in just a second. It's usually a fair call that if you are trying to describe something to somebody that you're doing in a maths course, there's usually a word for it if you need to try and tell someone about it. So, parts listing matrix, we've got that. Elements of the parts have numbers of items. Okay, so we have a demand. Okay, here we go. So this says that they had, company receives an order, and to fulfill, here we go. Company receives the order, and to fulfill the order, they calculate that they need to produce 4 sheds, 18 walls, 5 roofs, 23 aluminium sheets, 100 bases, and 656 bolts. Okay. So to fulfill the order, we need 4 sheds, 18 walls, 5 roofs, 23 aluminium sheets, 100 braces, and 656 bolts. Wow, okay. So they must have asked for 656 bolts straight up, because any other bolts they made are being used in here. That's my guess. Like, these are the primary items, they must be part of the order. That's my guess. Because we do have to make extra bolts, but we use them to actually make the roofs and the sheds. So my guess is that primary items are guaranteed to be part of the order, because they must have been asked for separately. That's what I'm going to hope for. Okay, and so then we're saying what was the order? So my reason to make a guess at what I think the answer, some part of the answer, is so that when I calculate it, I can have an idea of whether I've done it correctly. Okay. So in the notes it says that X is what they produce, QX is what you need to produce X, and D is the demand, which is supposed to be on top of all of the things that you need to produce X. Okay? So I'm going to put that in. So X is the actual production. Matrix times X is the parts needed for production. And D is the demand on top of this. So it seems to me that we have the production you make is the demand plus whatever you need to make the production. Because along the way you'll need to make, so I'm just thinking is to make, we've got 656 bolts and we're going to need 24 bolts to make each of those roofs, so 5 lots of 24, and we're going to need 24 bolts to make each of those walls, so 24 lots of 18, and we're going to need another 20 bolts to make each of those sheds, so 4 times 20. So that's how many bolts we actually produced. Like how many, yeah, okay. I could be wrong about this. No, other way around. Crap of all crap. I just want to read the question again. Okay. So do you think this 656 is the total number of bolts, including the ones in here? I think it might be. I might be reading this backwards.
Usually that would be separate.
Okay. Well, let's see what happens when we do this calculation.
Because with the examples, it's like that would just be 660 as a...
Yeah.
It would be that plus whatever was put into the...
All right.
Building the shed and stuff.
So you're saying yes, so that the actual order, right. So just a second. This list here is my x. Because we're asking what the order is. The order is the demand, right? So the order that is D, and they're asking us to find the order, so we need to find what D is. External demand sounds like an order from someone else who's asked me to make something. Okay, so I'm thinking that this is the order. Okay. And so we get x minus qx, which is I minus q times x. Okay. So the demand, which is what we want, is I minus q times x, which I could just figure out what that matrix actually is. Do you reckon I'm doing this right?
I think you meant to solve for x. So it would be x is equal to I minus q inverse times d.
You're really sure they want you to, in exam, figure out the inverse of this great big matrix?
So that's what we've been given. That's what we've been given.
I think we're looking for D, because it just seems natural to me that the external demand would be an order that you're given by other people to produce things. And so we haven't been asked, we haven't been told what the order is, we've been asked to find the order. And it says here in the actual thing, hint, remember that the order plays the role of the surplus demand in an open Leontief model. So we've been asked to, I didn't even notice that hint before, we've been asked to find the order and then been told that this is what the order is here, and we don't know what that is. That's what we've been asked to find. Because they said, what is that? So find this. Okay, cool. Which does mean, it's good because it means we don't have to find an inverse of a great big matrix during an exam. Okay, I reckon this is going to work. So I minus q would be minus q plus 1s down the diagonal. So I'm just copying my matrix here. Zero, 0, 1, 0, 0, 0, 1, 0. Like that. Okay? That's good. I minus q looks like a matrix that ought to have an inverse, so that's good. Not that we have to find the inverse, but just useful to know. I'm feeling like I'm on the right track now. And then the x was 4, 18, 5, 23, 100, and 656. Okay. We're going to try and make sense of this at the end, and hopefully it will make sense by then. So when I multiply this out, I end up with this times that would just be the 4, because it's mostly zeros. And then we have this times that. So minus 4 times 4 would be minus 16 plus 18, which would be 2, and all the rest of them are 0. Minus 4 plus 0 plus 5, which would be 1. 0. Minus 18 minus 5, we're now down to minus 23. Plus 23 is that. I'm going to have to do a calculator with that one. Minus 4 times 18. Minus 4 times 5. 0 plus 100, which is 8. And then we have minus 20 times 4, minus 24 times 18, minus 24 times 5, plus 656. That's the external demand. Now let's just check if this makes at all sense. So they wanted 4 sheds, 2 walls, 1 roof. They didn't ask for any plain aluminium sheets. They needed 8 braces and 24 extra bolts. Now, I want to see if I can make sense of this. 4 sheds matches the 4 sheds they asked for, because that's right at the top of my thing. So if they want 4 sheds, we're going to have to make 4 sheds overall, because it's right at the top of my little, I want to say like food chain, but not quite right. Okay, they want 2 walls, but in those 4 sheds, there's 16 walls already, and so total 18 walls have to be made. Ah, right, this is making sense. Okay, and they want 1 roof, but in those 4 sheds we're going to have 4 roofs, so that's a total of 5 roofs. Yes? Okay, that's how many we actually need to make. They didn't want any of these, but to do the aluminium sheets, we needed to get, there were like 5 aluminium sheets per this, which is 20, plus another 2 for those walls, another 1 for that roof, which is 23. It's all working correctly. Okay. It makes sense. Okay, so this is what they wanted, and in order to make that, we needed to produce these things. But overall, the things that we're really actually interested in, as far as the producer, is these things are the primary things we're going to need to produce in order to make what we want. And then we're going to collect some of them together to make walls and roofs. And then we're going to collect some of those walls and roofs together to make the 4. Oh, so it's my tree diagram backwards. I love it. Okay, this is so cool. I'm going to redraw my tree diagram because I don't want to ruin the one I had before. But right. I needed more space than that. Damn it. So what we're doing here is we're joining all these bolts together. And we're joining these braces together. And it's not going to be able to do what I want. So we're saying, I'm just making this up, so do this. So all of these bolts together, there's 656 of those. And all of these braces together, there's 100 of them. And all of these aluminium sheets together, there's 23 of them. But some of those 23 are part of walls, and some of them are part of roofs. And then there's some extra ones as well. Yes. Oh, I need a better diagram. I'm so happy that this is actually working in my head. It might not be working in yours, but I'm excited. Okay. Yes. Okay, so we have 656 bolts and 100 braces and 23 aluminium sheets. And then some of these bolts are being used. There's 24 left over. Some of them are going to be used to make walls, and some of them are going to be used to make roofs. And with the braces, there's 8 of them left over, and some of them are going to make walls and some of them are going to make roofs. And then the aluminium sheets, some of them are going to make walls and some of them are going to make roofs. And then and some of these bolts are used to join these together to make sheds. Yay! Okay. This is this diagram, but upside down. Yes. So there's 24 left over. There's 4 sheds total, so that's 4 lots of 20 braces, bolts. There's 4 sheds total, which means we need 4 of these walls, and 4 lots of 4 of these walls and 4 of these roofs. Yes. And so total number of walls that we need is 16, but they've asked for an extra 2. Yeah.
Sorry, how come on the other ones, like the other economic models that we do,
Mm-hmm.
we have to find the inverse, and it obviously works without finding it, but I don't know why.
So the reason I'm going to this is going to take me days to figure out what's going on here, I'm sorry. Luckily you have lots of time till your exam. Okay, I believe this. The reason why is because in the other problems you're being asked for the production, not for the demand.
Okay, right.
So in this question, you were told the production and you were asked for the demand, but in other problems you were told the demand and you're asked for the production.
So, like, if you want to find D, it's just I minus A or I minus 2 or whatever
Yeah.
times X, but if you want to find X, it's the inverse of I minus A times D.
Yeah. Like that. Is that what you just said? Yeah, so you've got to look really closely to figure out exactly what it is they're wanting you to do. So the interesting thing about this is that this problem's easier than the ones you've been doing recently, because the ones you've been doing recently require you to do inverses, and they've deliberately given you an easier problem in the exam that doesn't take as long to do, but because it's so different to what you've been normally being able to do, you might be thrown off and end up doing the long one anyway. So it's something to watch out for. Look very closely to see which parts of the information you've actually been given. And which parts you're trying to find. So traditionally you're told the demand to begin with, and you're supposed to figure out how much to produce in order to meet it. Yes, right. So I'm just going to go back a bit and see. I don't have an example. But in your classic Leontief model, you're normally told the demand. No, can't see it. All right. Well, I think that'll do. I think I'm wearing out, so I might stop there. Thank you for coming. Thank you for asking such excellent questions and giving me useful information to help everyone else. Maths Learning Centre is open until the end of exam period. So if you've got other questions about this or any other course that's got maths in it, feel free to drop in.